Well, then let me formally start. I will be talking about Kähler-Einstein metrics in algebraic geometry. So there's a long history of interaction between complex analytic geometry and complex algebraic geometry, and certainly the theory of Kähler-Einstein metrics has definitely been a big actor in playing an interaction in between those two fields. And so I would like to somehow summarize over the course of the last maybe 40 years, which kind of striking applications Kähler-Einstein theory has had in the field of algebraic geometry. So I've selected quite a few, let's say, particularly interesting results in algebraic geometry that were derived using Kähler-Einstein metrics, and of course there are many more that exist, but I've decided to focus on those examples. So I'll get back to that later. The way I've essentially split the two lectures, more than two separate lectures, it will be really a continuing one. And the first half, so I will certainly take some time to introduce all the necessary material, so basic notions of what Kähler metrics are, Kähler-Einstein metrics, and the big existence theorems due to by Yao in the late 70s. And then I'll focus a little bit in a second time on Fano manifolds. And eventually I will move on to, as I was saying, several striking applications of Yao's theorem and his corollaries to, so on one hand, the uniformization theorems. So how can we tell from numbers whether a variety is covered by a projective space, a ball, or a CN? Now I'll move on to a slightly different type of results involving stability of the tangent bundle. Okay, so for Kähler-Einstein manifold, the tangent bundle enjoys some very specific stability properties. So I'll explain that, and from there I'll move on to splitting theorems. And in the last part, I will also touch on just a little bit some recent progress on generalization of the theorems that will have been explained from section 1 to 5 to the case of singular varieties. And there will certainly be, this will certainly be very nicely complemented by Daniel's lecture. Okay, so let me start. Very basically, what is a Kähler metric? So throughout the talk, X will always be a complex manifold. In order to simplify some definitions, or I will always assume that X is compact. Okay, the definition of Kähler metric has nothing to do with compactness, but certainly for compact manifolds, the existence of a Kähler metric is a strong constraint. So a Kähler metric is a differential form of by degree 1, that satisfies two local properties. The first one is that it's D closed, so D omega is 0, and the second one is that omega is positive. Positive, probably the easiest way to understand what that means is whenever you write omega using a local system of coordinates, Z alpha, then omega can be described by n by n matrix, omega alpha beta bar, which is Hermitian, and omega is positive if and only if the Hermitian matrix is definitely positive. Okay, so this is the definition of a Kähler metric, which is a certainly local definition, but there are global obstructions for the existence of such a metric on a given complex manifold. Very simply, maybe the simplest example in the compact case would be the flat metric on CM that is certainly invariant under any translation. Okay, because when you change z alpha and you replace it by z alpha plus a constant, the differential form dz alpha is invariant under that change of coordinates somehow. And so the Euclidean metric descends to any torus. Because Cn mod lambda, well, lambda is a lattice. So I want to observe very early on that even though a compact complex manifold may not admit a Kähler-metric, once you have one single Kähler-metric on a compact complex manifold, then automatically you have a lot of them. Essentially, being Kähler is an open property in the suitable vector space. And so if you have a Kähler-metric, you have all of them. And one of the main themes, one of the recurring themes in my talk will be that we want to look for a Kähler-metric that's better than others, which doesn't mean much. Sometimes people like to say that they're looking for canonical metrics. So metrics that satisfy additional properties that make them maybe unique or unique up to some biomorphism and satisfying a certain nice equation. So this is the object of this talk, and that will involve defining the Ricci curvature of a Kähler-metric. The definition is a little bit ad hoc, but the point is there's a notion of Ricci curvature for any Riemannian manifold, certainly, and when you apply that definition to a Kähler-metric, the formula actually becomes much easier. And so you can take this as a definition that the Ricci curvature of a Kähler-metric, omega, is just minus I dd bar of the log of omega to the n. So this formula would probably could make you think that the Ricci curvature is always d or d bar exact, but this is not the case because log of omega to the n is not a globally defined function. It's only defined locally. But fortunately, when you use two different set of coordinates, the difference between the two functions log omega n is a pluriharmonic function, so the difference clears out when you take the dd bar. Okay, so just to say, Ricci omega is minus I dd bar log of the determinant of the matrix in a coordinate system. Okay, so a few properties, very elementary properties of the Ricci curvature of a Kähler-metric. So the first of all, as I was saying, this is well defined, even though log of omega n doesn't make sense as a function. Taking its dd bar is actually a well-defined differential form of by degree 1, 1. And obviously it is closed, right? Because it is locally exact. The second property is crucial, and is that the cohomology class of the Ricci curvature of a Kähler-metric, omega, is actually independent of the metric itself. Okay, it defines a unique cohomology class, no matter which Kähler-metric you choose. And this class coincide, maybe I would have needed to use some, let's say, factors, maybe multiplicative factors, but normalization factors, but let's drop that. So I'll just assume that the cohomology class of Ricci omega is the first term class of X. So living in the H2, in the second cohomology group of X. And again, it does not depend on omega. Third property, which is somehow very closely related to the second one, is that you can see the Ricci of omega from the very definition. It arises as a Chern curvature of the Hermitian bundle that is obtained by taking the determinant of the tension and endowing that with the metric induced by omega, so omega to the n. Okay, so that's about the Ricci curvature. Now let's move on to Kähler-Einstein metrics. Again, X omega compact Kähler manifold, and I define omega to be Kähler-Einstein if the Ricci tensor, which is a 1-1 form, is proportional to the form itself, to the Kähler-metric omega. So there exists a constant, a real number lambda, such that Ricci omega equals lambda times omega. Okay, that's a very neat equation called the Einstein equation. And since we require omega to be Kähler, we can call this the Kähler-Einstein equation. A remark that will not be that crucial is that if you change omega to a multiple of omega, the Ricci curvature of omega doesn't change, right? Because you take the IDD bar of log omega n. And because of that, if you scale omega, you can, if you start from a Kähler-Einstein metric omega and you scale it, you can eventually obtain still a Kähler-Einstein metric, but where the Einstein constant is either -1, 0, or 1. Okay, so just to say that the number itself, lambda, is not very important. What's important is the sign, whether it's positive, negative, or 0. And this is very closely related to the geometry of the variety, as I'll get to in a second. Okay, the first basic examples. So somehow the paradox is to exhibit a Kähler-Einstein metric. It's not that easy unless you exhibit something that's even better than a Kähler-Einstein metric, and that's a metric with constant curvature. So, and you can do that on very symmetric spaces, homogeneous spaces like Pn, tori, or Boole quotients. Okay, so I've written down the expression of a Kähler metric on each of these spaces, or at least you can write it down on the universal cover and check that the metric is actually invariant under the fundamental group, any group of automorphism. And so it descends to the compact quotient. Okay, so those metrics have constant curvature actually in the holomorphic sense. And so in particular, taking the trace, they have certainly constant Ricci curvature. Okay, and so Pn has the Fubini-Studi metric, which is positively curved. The flat metric on Cn descends to a flat metric on the torus. And finally, the Bergman metric on the ball, the unit ball in Cn, is invariant under any automorphism of the ball, and so it descends to any compact or not quotient of the ball, and to a Ricci Kähler-Einstein metric with -1 curvature. Okay, so let me move on to the very first step. Like, we want to see if we can find a criterion that guarantees that a certain manifold admits a Kähler-Einstein metric. The first obvious obstruction to existence, okay, short answer, not all compact Kähler manifolds admit a Kähler-Einstein metric. Actually, only very specific manifolds do. And the first obstruction lies in the homology of X. Okay, so, right, so I recall here the definition of Kx will show up quite a bit in this talk. So Kx is just the line bundle of top degree homomorphic forms. And you can also see it as the determinant of the cotangent. And the Ricci curvature of omega, as I was saying, belongs to the same cohomology class no matter what metric you choose. And this is the first Chern class of X, which is the same thing, but the normalizing factor is the same thing as the Chern class, first Chern class of Kx. Now let's say my manifold admits a Kähler-Einstein metric omega. So certainly, combining the observations above, I get that minus lambda omega belongs to the first Chern class of X. And because of that, it means that, because omega is scalar, it means that the cohomology class, first Chern class of Kx is either positive, negative, or 0. Okay, so it has a sign, which is a strong constraint. Okay, because having a sign by Kähler-Einstein theorem, at least for a positive and negative sign, it implies that Kx as a line bundle is either anti-ample if lambda is positive, numerically trivial if lambda is 0, and ample in the negative curvature case. Okay, so this tells me that if X admits a Kähler-Einstein manifold, then it belongs to one of the following 3 categories that are disjoint. Either X is Fano, X is Calabi-Yau. So I use the terminology Calabi-Yau for a manifold with numerically trivial canonical bundle. Or X belongs to the extreme opposite of the spectrum. X is a canonically polarized manifold, meaning that Kx is ample. So those are the necessary conditions for X to admit a K metric, is that it belongs to one of those three types of manifolds. Let's talk about examples of such manifolds very briefly. I'm sure you are all aware of these very standard example. If you take an hypersurface in Pn of degree G, smooth hypersurface, and then it turns out that the canonical line bundle is either negative, 0, or positive according to the degree D. Okay, so you automatically land in one of the three classes that I was mentioning above. And so if the degree is small enough, you're Fano. If the degree is exactly the dimension of Pn plus 1, then xd is going to be O. And then after that, if the degree is larger than plus 1, then xd is canonically polarized. Okay, and one question you may want to ask is, okay, I take an hypersurface in Pn. Can I find a Kähler-Einstein metric since the cohomological obstruction are not present or are satisfied, the cohomological constraints are satisfied for each of these manifolds. And so you may wonder whether or not XD is canonical. Well, I'm going to answer the question, or partially answer the question in the following slides, and much more general setting. So I'll start with the negative sign. So the first theorem was proved simultaneously by Aubin and Yao independently in 1978. And it says that if you start with a manifold whose canonical bundle is ample, meaning that X is canonically polarized, then there is a unique metric omega that is scalar and that satisfies the equation Ricci omega is minus omega. So any canonically polarized manifold emits a unique K metric. Strike.
Nikon, can you turn Fedor's mic off, please? Nikon.
All right, thank you. Then we move on to the second result, the celebrated theorem of Yao, actually proven in the same paper as the one, the result above in the canonically polarized case. So Yao's theorem says that we can always solve the equation Ricci omega equals eta as long as eta lives where it's supposed to live. Okay, so the precise statement I gave here, it's you start from a differential form in the cohomology class, first string class of X, and you pick your Kähler class. The Kähler class is just there to ensure uniqueness. And then Yao's theorem tells you that you can find a metric omega that's unique as long as it belongs to the Kähler class alpha, and that solves Ricci omega equals eta. So this theorem is extremely powerful, and most times people extracted of this result its celebrated corollary that whenever X is Calabi-Yau, so whenever C1 of X is 0, then you can solve the equation with eta equals 0. Which tells you that for Calabi-Yau manifolds, as soon as you pick a Kähler class, there exists a unique Kähler metric inside that class, which is Ricci flat and Kähler. Okay, so this is the first theorem that provides Ricci flat metrics in a very broad setting. Even in, like, if you forget about the Kähler condition, in differential geometry, it's really hard to produce Ricci flat Riemannian metrics. And I think Yao's theorem is really the first example of like non-highly symmetric varieties where we can exhibit a large class of examples of Ricci flat metrics. It's quite impossible to understate the importance of that theorem, the impact it had on complex geometry in the years that followed, even up until now. And so as I was saying at the very beginning, this talk is dedicated to explaining what kind of applications this particular theorem or those two theorems had in complex geometry. And I took essentially three different classes of examples of applications. So one is on finite manifolds, the second one uniformization theorem, and the last one on stability of the tangent bundle, which are quite of a different flavor. And so that will already give you an idea of how influential Yau's theorem has been in complex geometry. Let me talk, so maybe let's go back to this slide for a sec. Right, those two theorems in red, it treats the case of negative curvature, zero curvature. So what about positive curvature, which corresponds to finite manifolds? Does a finite manifold always admit a Kähler-Einstein metric? The question is left open by those two theorems. The truth is we've known for a while, right, at least in the 50s, that it's not true. A finite manifold may not admit a K metric. And finding exactly what additional obstructions exist as taking has been very important, and people have had a hard time really narrowing down the exact condition that would guarantee existence. So adding more obstructions to eventually get a criterion for existence. But anyway, so one obstruction lies in the automorphism group of the manifold. Okay, Matsushima proved that finite manifold, that is Kähler-Einstein, has an automorphism group that's reductive, kind of complexification of a compact real group. So this is certainly not the case for the blow-up of P2 at one point, and so that finite manifold does not admit a K metric. In terms of uniqueness, the situation is as good as it can be. They're not unique. They're not unique as in the negative curvature case, but somehow they are unique up to biomorphism. Certainly if you have a Kähler-Einstein metric and you pull it back by biomorphism, this will still be Kähler-Einstein with the same constant. But it may not be the same metric anymore. Okay, you have explicit examples like in PN, for instance. Now let me go back to the case of an hypersurface that I've left open, right? An hypersurface of degree less than +1 is always final. And to my knowledge, there is no general result that says this hypersurface is Kähler-Einstein or not in every situation. So there are lots of isolated cases that are known. Certainly when for surfaces, we have a characterization of del Pizzo surfaces that are Kähler-Einstein, and so you can check whether or not that happens for hypersurfaces. It's quite easy for hypersurfaces that are del Pizzo. And then you have isolated examples like the Fermat hypersurface that is always Kähler-Einstein, and small degrees, large degrees, we also have existence of a Kähler-Einstein metric. Okay, so that's all I'm going to say about non-existence of Kähler-Einstein metrics on the finite manifold, but it is a very active area of research, and there have been beautiful developments in the last 5 to 10 years, but I won't have time to mention any of that. Okay, so this slide is here to essentially introduce what's going to happen in the following slides, in the next few slides. I want to explain why and how we can make use of Kähler-Einstein metrics to deduce some properties on the manifold. So the general scheme is that you start from a manifold, and you have to assume at some point that X has a particular geometry, usually involving positivity type condition on the canonical bundle. Something that enables you to essentially get to the existence of either a canonical metric or something close to that, right? Like typically it would be omega would be Kähler-Einstein, but not necessarily be approximately Kähler-Einstein, or you can have like Ricci curvature kind of a sign, and so on and so forth. But what I'm saying is you want to go from a geometric intrinsic assumption on X to the existence of a special metric, omega. And with that metric, you want to make use of the fact that you have single data metric to analyze the geometry of Tx using differential geometric methods, now that you have a metric to work with. Okay, and you may want to derive some results about the geometry of X, and that can be either from a topological point of view, okay, so try to analyze what the universal cover of X is, or try to give restriction on the fundamental group of X, maybe tell something about the Turing classes of X, and so on and so forth. So either topological properties or finer analytic holomorphic algebraic, if you start from projective manifolds, properties. And so here I've mentioned just a few generic examples, like say something about the stability of Tx, or if X can be split as a product of two manifolds, or what can be said about the Lie space of certain manifolds, or deformation space of X, and so on and so forth. Okay, so this is a general scheme. Go from information on Kx to global information on Tx using a canonical metric. So the first example of that that I want to give dates back a while, and it's an example that I like because it mixes a lot of interesting techniques. It's the following theorem. The following theorem tells us that a Fano manifold is simply connected. So there are lots of proofs of this statement, but I want to explain to you how you can deduce this statement from Yau's theorem. Keeping in mind that a Fano manifold is not always Kähler-Einstein, so I'm not going to use Kähler-Einstein metrics, of course, but this is where somehow the force, the strength of Yau's theorem is, not just the existence of a Ricci flat matrix, but the fact that we're able to solve the equation Ricci omega equals eta.
So the original proof is by Campana, if I remember correctly, right? Using rational curves or something.
So one of them, yes. So Campana actually proves that X is even rationally connected, which is stronger certainly. I think Kähler-Einstein may have proved the same statement as well. But yeah, so the proof that I want to explain is, I think, due to Kobayashi. At least Kobayashi observed that we can deduce that statement if we know that there's a Kähler-Einstein metric. And at the time, we didn't have that. But I mean, if we know that we have the solution of the Calabi conjecture. Sorry. Okay. So here's a proof. Here's one proof. So the first step, as I was saying, so you make an assumption on the geometry of X, which is X is Fano. So Kx minus Kx is ample, because minus Kx is ample. Yau theorem tells you that you can find a Kähler metric whose Ricci curvature is positive, because you pick the positive representative of the first Turing class of X, which you can always find since X is Fano, and then you solve the equation Ricci omega equals that representative, and that will give you the positively curved Kähler metric. Okay, so because X is compact, if Ricci omega is positive pointwise, well, certainly Ricci omega has to dominate a small multiple of omega itself, okay, just by compactness of X. So Yau theorem tells you, okay, I start from a Fano manifold. Maybe it's not Kähler-Einstein. Maybe I cannot solve Ricci omega equals omega, but I can solve Ricci omega equals something that's larger than a small multiple of omega. Okay, that I can always achieve. And why is this good news? Because this condition is invariant when passing to the Riemannian universal cover, right? So here I call X tilde omega tilde the Riemannian universal cover. So omega tilde is just pi star omega, right? And the condition that Ricci omega is larger than epsilon omega pulls back to the same condition on X tilde. And this time X tilde might not be compact anymore, right? I've taken the universal cover. There's no reason why X tilde would be compact, but it's certainly complete, okay? Because a cover of a complete manifold is complete. Being compact is certainly stronger than being complete. So certainly the universal cover X tilde omega tilde is complete, and the Ricci curvature of the pullback of the Kähler-Metric omega is larger than epsilon. And then there's this well-known theorem of Myers, generalizing a former result of Bonnet, that says that if you have a complete Riemannian manifold whose Ricci curvature is strictly bigger than a positive constant, then your space is compact already. And this is also bound on the diameter and so on and so forth. So this tells me that the universal cover of X is compact, but that can only happen if pi1 is finite. Okay, meaning that the universal cover is a finite map and pi1 of X is finite. Okay, so what I get combining Yau's theorem and Bonnet-Myers theorem is that maybe my Fano manifold is not simply connected at this point, but its fundamental group is finite. And once you're there, things get much easier because you can use algebraic tools. So the first observation is that X tilde being Fano, right? The universal cover, finite étale cover of a Fano manifold is Fano. And so the holomorphic Euler characteristic by Codera vanishing is 1. Okay, all the HP of OX for X Fano vanish, okay, because minus KX is ample. So it says that both the Euler characteristic, the holomorphic Euler characteristic of X and X tilde are 1. Okay, and now the last nail in the coffin is Remineral Theorem that tells me that the Euler characteristic actually behaves well under finite étale morphism, meaning that it's multiplicative. Okay, and then you put everything together and you see that necessarily the degree of the universal cover is 1, which means that X tilde is biholomorphic to X, and that also means that X is simply connected. Okay, so this is a very neat proof, right? It can fit in one slide, but when you look at the blue names, there's a lot of deep mathematics involved and from very diverse horizons. So to me, that's what makes it really striking and somehow compelling application of Yau's theorem. Okay, so that's the first application that I chose of Yau's theorem, existence of Kähler-Einstein or sort of Kähler-Einstein metrics. Now I want to move to a type of application that has quite a different feel. And so it's, I want to explain Miao-Yau inequality and the uniformization theorems. So the story starts pre-Yau somehow. Is the following computation that's due to Chen and Ogui in 75, if I'm correct, that says that if you have a compact manifold and if there exists a Kähler-Einstein metric, you don't care about the sign at this point, then the Chern numbers of X, the first two Chern numbers of X, C1 and C2, have to satisfy some inequality. It cannot be arbitrary. Again, the equality is the one that I wrote down. So 2 times n plus 1 C2 of X minus n C1 of X squared times paired with alpha to the power n minus 2 is non-negative. So it's a so-called Miao-Yau inequality, but I'll get back to that in a second. Okay, alpha is just a cohomology class of the Kähler-Einstein manifold, and more importantly, it's actually the equality case is really interesting, it says that you have equality if and only if universal cover of X is Pn, Cn, or Bn. Okay, so this is why you can consider this as a uniformization theorem. Of course, it's not very satisfying because this is assumption that X has to be Kähler-Einstein, and this is not something you want to assume. This is not a very reasonable assumption to make, but again, and we'll get back to that in a second, thanks to Yao theorem or Yao theorem, this is an assumption that we can rephrase in a much more convenient way, much more easily checked. Okay, I want to explain where that comes from, this inequality. So the idea of the proof, again, is, as I was highlighting earlier, we have this assumption. So here the assumption is directly that X is Kähler-Einstein. Okay, so I skip the geometric assumption leading to the existence of a special metric. I already have my special metric at hand. But now that I have this metric omega, it induces an emission metric on Tx. And now I want to analyze the geometry of Tx using this metric. And in particular, I can compute the Chern classes of X using the representative Ci of X omega that are induced by the metric omega. Okay, the first Chern class do not, the first, second, all Chern classes that don't depend on any choice of metric, but to compute them, it's convenient to choose a representative. And here I have very conveniently a representative that's given by the first Chern class of X, first or second Chern class of X omega, where omega is Kähler-Einstein. Okay, so that's the idea of the proof. Now, how does it exactly go? Here is explained here. So it's essentially the theorem of Chen and Ogue. It's the formula that is in the middle of the slide, right? It's a very long formula. So let me try to explain what everybody is. On the left-hand side, so I have taken the first, second Chern class of X omega, and I've done this linear combination of C2 and C1 squared with respect to omega, and I wedge it with the Kähler-Einstein metric omega to the power n minus 2. So on the left-hand side is somehow a pointwise expression of the quantity that appears in the theorem. Okay, but this is a differential form. So this is really, this is not at the cohomological level at this point. And on the right-hand side of the inequality, I've got a difference of two non-negative terms. Okay, and this is the contribution of these guys, is that you can see that there's a positive contribution and a negative contribution, and you can somehow express them in terms of the curvatures, various curvatures of omega. I'm not going to detail exactly what those terms are, but what's important to know is that for us, being Kähler-Einstein is equivalent to the traceless Ricci omega being 0. Okay, so of course the traceless part of Ricci is what appears with a negative sign on the right hand side, and so this is the bad term from our perspective. And so if omega is special in the sense that it is Kähler-Einstein, well, the bad term disappears and I'm left with a non-negative term, and that's very convenient, because then I can integrate and suddenly I get my inequality. But better, okay, because if I have equality, it means that the term that I've thrown away, and that's always non-negative, non-positive, its integral is 0. So that can only happen if pointwise my term is 0, okay, and that term in question is the traceless part of the bisectional, homomorphic bisectional curvature. And so the equality case can only happen if omega is constant homomorphic bisectional curvature. And it's been known forever that such a Kähler-metric has universal cover, either Pn, Cn, or Bn. Okay, so there we go. There we can uniformize X. using a metric characterization. Okay, so how do I use this theorem of Chen and Gouillet? So that's the object of the next slide. So if X is compact Kähler manifold, then I have three cases. Okay. Fano, Calabi-Yau, canonically polarized. I'm going to go through each of them. So if X is Fano, it may not be Kähler-Einstein, right? As I've explained earlier, there are counterexamples. So I have to assume, and that's the downside of it, I have to assume that X admits a Kähler-Einstein metric. Okay, so I assume that X is Fano and Kähler-Einstein. How can I guarantee that? I don't know. Maybe I have a God-given Kähler-Einstein metric and I want to know more about X. Well, in that case, I know from the formula above that I have Miao-Yau inequality, meaning that 2 times n plus 1 C2 minus n times C1 squared against the C1 of X to the power n minus 2. This is always non-negative. And if equality occurs, then X is automatically a projective space. Okay, so you can see this as a uniformization theorem. This is a uniformization theorem where to guarantee that X is Pn, I have to check 3 conditions. First one is that X is Fano. This seems like a reasonable condition, right? The second one is that X is Kähler-Einstein. So that's already harder to check, but let's say we can do that. And the third one is topological. I compute this Chern number, which is this polynomial in the Chern classes C1 and C2. And if it's 0 if and only if my Kähler-Einstein Fano manifold is just Pn. Okay, so here's a nice characterization. There are 1,000 of different characterizations of projective space. Here's one of them that involves Kähler-Einstein metrics and Chern numbers. Okay, so the slightly disappointing part is that the assumption that we have to assume X is Kähler-Einstein to start from. In the last 2 cases, because of Yau theorem, this is not an assumption that I have to make. Okay, it's automatically fulfilled. Okay, so if X is Calabi-Yau, then I know by Yau theorem that X admits several Kähler-Einstein metrics, Ricci flat. And so it will satisfy my Chern number inequality, but certainly the C1 of X is 0, so the inequality becomes much simpler somehow. It says that C2 is semi-positive in some sense, the sense being that it's semi-positive against any n minus 2 power of a Kähler class. And better, if I can find a Kähler class, alpha, such that C2 of X against alpha to n minus 2 is 0, then automatically X is a torus. And that's an if and only if. Okay, certainly for a torus, all Chern classes vanish. But the surprising condition is that if X is Calabi-Yau, then X is a torus if and only if C2 is 0. Okay, so this is somehow a real uniformization theorem in the sense that you start from a variety that has numerically trivial, or that has first Chern class and second Chern class 0, then automatically, if it's scalar, that variety is a torus. The last case is the case of negative curvature, or positive Kx, if you prefer. In that case, Aubin and Yau theorem tells me that X always admits a unique Kähler-Einstein matrix. So again, I can apply Chen-Gouillet theorem from before and get the Chern number inequality that I wrote down, 2n plus 1 C2 minus n C1 squared against Kx to the n minus 2 is non-negative. And 0 if only if X is uniformized by the ball. I want to make 2 slight historical comments about those inequalities. First of all, if X has dimension 2, you observe that the n minus 2 is 0, okay? And so the inequality really becomes 3C2 is larger than C1 squared. And this is an inequality that Miałka proved in a very general setting, initially for non-uniform surfaces, and eventually generalized that to non-uniform varieties in a very general setting. Okay, but that inequality with 3C2 is larger than C1 somehow is weaker than the Miałka-Yau inequality as soon as n is at least 3. Okay, you can do the computation, compare 2 times n plus 1 over n, compare that in 3, and you'll see that there's an inequality that's always strict as soon as n is at least 3. And so this is why it's called Miałka-Yau inequality. Somehow this should really be called Yau inequality in any dimension. In dimension 2, it's the same thing as Miałka inequality, yet Miałka inequality applies to a wider class of varieties. Okay, so that's why usually those two names are put together, but really those are two different inequalities that are a very similar flavor. Okay, so that's all about uniformization theorems. So in Daniel's talk and talks, in his lectures, he will tell you much more probably about those uniformization theorems, also in the case of singular varieties. So yeah. Okay. So the next topic that I want to touch on is about stability of the tangent bundle. And here again, it's something that's very much of a different flavor compared to the other two applications of existence of Kähler-Einstein metrics, both for a simple connectedness of panels and the uniformization theorems. So here, let me start by recalling, I'm sure most of you know already all about it, but to be short, let me recall the definition of slope stability. So it's a notion that's been introduced by Mumford and Takemoto a while ago, and it was introduced because as a property that guarantees that certain families of holomorphic bundles over curves have good moduli space. Okay, but this initial motivation for introducing the condition, the slope stability condition, turns out to be certainly very important, but also the stability itself had many more applications that are in some sense way not so related to the initial motivation of moduli spaces of sheaves. So the definition rests on the notion of a slope of a bundle over a sheaf. So if you have a holomorphic bundle in a compact complex manifold, and if you fix, let's say, a Kähler class, then the slope of E with respect to alpha is the quotient of C1 of E against alpha to the n minus 1 by the rank of E. Okay, so that may seem a bit odd. So slopes behave in a very natural way with respect to short exact sequence and so on and so forth. I won't get into that. Let me just cut short and define what a stable bundle is. So a stable bundle is a bundle such that any of its proper subsheaves, F, so by proper I mean that F is not 0 and the rank of F is less than the rank of E. Okay, I don't want to have subsheaves that are not saturated, for instance, and with top rank. So I want to say that E is stable if for any proper subsheaf, the slope of F is less than the slope of E. Okay, very simple definition. If you see it for the first time, it's maybe a bit weird, define that, but why not? Bear with me. And then I said that E is semi-stable if I have the same property, but I can relax the inequality to a non-strict inequality. And then there's a notion that sits somewhere in between stable and semi-stable. That's called polystable. And a bundle is said to be polystable if you can write it as a direct sum of stable bundles. If I just said that, a direct sum of stable bundles might not even be semi-stable. So this is not quite satisfactory. So I define E to be polystable if E is the sum of stable bundles with same slope as E. Okay, an equivalent definition, if you prefer, you can check. It's quite straightforward to check that this definition is equivalent to E being a sum of stable bundles and that E is semi-stable. Okay, if you assume both conditions, you can check that automatically the slope of the EI is equal to the slope of E. Okay, so that's the definition of a stable bundle and polystable bundle. All right, here's the theorem. It was proved by Kobayashi-Lübke, and it's somehow half of the so-called Kobayashi-Chin correspondence, but it really is the easy direction. The Kobayashi-Chin correspondence states that a vector bundle in a complex Kähler manifold is polystable if and only if the bundle admits a certain canonical metric called Hermitian-Einstein. When you specialize this to the case of Kähler-Einstein manifolds, then you get the statement that I'm about to explain. Okay, so this is why sometimes people refer to this as half of Kobayashi-Chin. Okay, here's the statement. So as usual, I start with a compact manifold, and I assume that X can be endowed with a Kähler-Einstein metric. So for instance, X is Kähler-Biot, or X is canonically polarized, or X is Fano, and you know for some reason that X admits a Kähler-Einstein metric. Okay, and for simplicity, I want to denote by alpha the cohomology class of omega in the H11. Okay, so that alpha, if X is Fano, would be C1 of X. If X is canonically polarized, it would be C1 of Kx. And otherwise, in the Kähler-Biot case, it could be anything, any kind of class. And the statement is that Tx is polystable with respect to alpha. And actually, you can be much more precise. So you can write, so the polystability means that Tx is a sum of stable bundles. Okay, so the Fi's are stable with respect to alpha with the same slope as Tx. So if I just said that, it means Tx is polystable. But actually, I can say much more from a differential geometric point of view. What else can I say? Well, the Fi, they're not completely random or arbitrary. They are parallel with respect to omega. So what it means is that they're preserved by parallel transport. Or if you prefer, if I take a vector field, right, that lies in Fi, okay, and I want to differentiate this vector field with respect to any tangent vector, then a priori, when I differentiate using the covariant derivative induced by omega, when I differentiate this vector field that belongs to Fi, I might get another vector field that may have nothing to do with Fi. Now, the fact that Fi is parallel means that actually this does not happen with those guys. So whenever I differentiate a vector field in Fi, and using the covariant derivative induced by omega, then I remain in Fi. Okay, which is again equivalent, if you prefer to think in terms of parallel transport, it means that if you pick a vector in Fi at a point and you do the parallel transport along the loop that you fix, And then by the time you go back and end the loop, the new vector that you get in Tx is also in Fi. Anyway, so that property implies in particular a slightly less strong property that the Fi's are foliations, meaning that they are preserved under the Lie bracket. If I do the Lie bracket of Fi and Fi, I'll end of two vector fields in Fi, I'll end in Fi again. Last property is that these Fi are orthogonal with respect to my Hermitian metric omega. Okay, so really what I get is a decomposition of Tx in terms of mutually orthogonal subbundles with maximal slope, stable, and that are parallel. Okay, so this is the content of Kobayashi-Lübke theorem. The existence of a Kähler-Einstein metric on a compact manifold implies that the tangent bundle is very special. It is the sum of parallel bundles. So rather than rushing through the proof of that statement, I think I would rather stop here, and tomorrow I'll go through the proof. And yeah, so I'll finish this application about stability, and then I'll move on to from stability to splitting theorems. And in the remaining time, I explain okay, what happens when X is singular. But for now, I think I will just stop here. So thanks for your attention.
Thank you.
Thank you. Yeah, any questions?
So it's a cliffhanger, right? It's too early to ask questions.
Maybe I have a question.
Mm-hmm.
It's about the other applications, the other implication of the Kobayashi-Hitchin correspondence. So in the case of a Farner manifold, if the tangent bundle is say stable,
yeah.
Then you get something like so it is. So is it true that you have a Kähler-Einstein metric in this case?
I don't think so, but can't give you. I don't have an example right off the top of my head. I would be surprised if this were true, because usually the characterization of Kähler-Einstein metrics is much more involved than just the stability of the tangent. I'm sure there are counterexamples, I just can't think of any.
I see. And so what does the Kobayashi-Hitchin correspondence tell you in this case?
So
in terms of metrics, I mean.
So the weird, the slightly, let's say, okay, let me say that. So if Tx is stable, Kobayashi-Hitchin tells you that Tx admits a Hermite-Einstein metric, right? The thing is, if you have a Kähler-Einstein metric, it induces Hermite-Einstein metric on Tx. But if you have an Hermite-Einstein metric on Tx, it has no reason to come from a closed positive form on X. So having an Hermite-Einstein metric on Tx doesn't tell you anything about whether or not there might be a Kähler-Einstein metric. It's much weaker somehow.
I see. Okay.
Yeah, but it's really subtle. Like there's this miracle that in Kähler geometry, the tensor, the Ricci, the curvature tensor is very symmetric, and so if you have a Kähler-Einstein metric, it induces an Hermite-Einstein metric on Tx. But that's because the curvature tensor of Kähler metrics are very particular. But if you only know that you have an Hermite-Einstein metric on the tangent bundle, there's no way you can recover a meaningful Kähler-metric on X in general.
Yeah, I see, because the curvature tensor is kind of mysterious in that case.
Right. I mean, from H, it's not clear how you get an actual closed 1-1 form. You certainly get a 1-1 form out of H, but that it's closed there's no obvious reason why that would happen.
And then you get a connection, but there is no reason it should be torsion free, right? So it's not the Levy-Civet or anything.
Right. Exactly.
I see. Okay, thank you.
Yep.
So, okay, I think if there are no more questions, let's thank speaker again. And